And we are back. All right, today we're going to talk about the atomic spectrum of hydrogen, which is not a continuous spectrum. Okay, a continuous spectrum is one in which white light is passed through a prism, and literally you see the entire continuous spectrum. If you remember the Roy G. Biv, which from left to right is opposite that in terms of increasing wavelength. So with the spectrum of hydrogen, it is what's called a line spectrum. There's only certain lines at discrete wavelengths. Okay, and how we get this is hydrogen gas receives a spark, and those hydrogen molecules absorb energy. Those atoms get excited and emit light of different wavelengths. So as opposed to the continuous spectrum here, where we have all of the different colors of light, instead, with hydrogen gas, which a voltage is applied to it, it gets excited, we only see 4 distinct lines. One violet or purple, one blue, one turquoise, and one orange. So this is what's called a line spectrum. So what those lines indicate, the result of that means that only certain energies, meaning certain energy levels, are allowed for an electron in the hydrogen atom. So this helps support the Bohr model and the fact that energy is quantized. Okay? Because each of these wavelengths corresponds to a different color, and only certain colors are permitted. So if you remember from class yesterday, the change in energy is equal to H, which is Planck's constant, is always the same, times the frequency, times nu, the frequency of that light, or, remember, we can rearrange it in terms of wavelength, so it's Hc over wavelength. Okay, so since there are only certain wavelengths of light, according to this diagram, 410, 434, 486, 656, that means that only certain energies are permitted, meaning that energy is quantized. Think about the ladders on a step. And if you remember from the firework example I gave, remember different atoms have different distances between the ground state, the lowest energy ground state, and each of these higher energy excited states. Okay? And these certain distances, like this distance here, corresponds to a certain wavelength, which corresponds to red, whereas this distance corresponds to green and blue, and so on. So that's why different atoms correspond to different colors when they're excited, when they get exposed to a flame, and then that's why in hydrogen you see these different lines. One of these lines represents, one of the lines on the line spectrum corresponds to the electron jumping down from the second to the first energy level, or from the third to the first, or the blue is from the fourth to the first. So that's how we get these different lines in this line spectrum. Okay, so each of these energy level jumps corresponds to a different line on the line spectrum, and that indicates that only certain energies are possible. Okay, so this is very significant that the hydrogen emission spectrum is not white, because if these levels were not quantized, we'd see the white light because all possible energies could be released. So all possible colors emitted means that it will be white light. It'll be that continuous spectrum. But that line spectrum means that only certain energy values are possible. Okay, then the emission spectrum supports the idea of quantized energy levels, since only certain colors are observed. So, with the hydrogen spectrum, we have the 4 distinct lines on the line spectrum. So this right here supports the Bohr model, the fact that those energy levels are quantized, that energy can only be in certain energy levels. And an electron can exist in one level or another, but electrons can't exist in between two levels. Like, it cannot exist between the first and the second level. Okay, and with the Bohr model, the electron in a hydrogen atom moves around the nucleus only in certain circular orbits. And if you remember from the online activity you did, the particle in motion tends to move in a straight line. If you remember the one model, the electron went straight into the proton. And normally you would think that would make sense because opposite charges attract. The negatively charged electron would be attracted to the positively charged proton. But also we have to balance with the fact that electrons want to fly off, the tendency for an electron to move in a straight line and fly off. So those two tendencies are balanced, and since it orbits the nucleus, the electron has a constant acceleration. Okay, so only certain orbits are allowed, and that's consistent with the line spectrum. And how we label these different states, the ground state, the lowest energy state, the one closest to the nucleus is n equals 1. Then, as we get farther and farther away from the nucleus, the higher energy levels, we just label those with whole numbers. So like as we get farther and farther away from the nucleus, n equals 2, 3, 4, and so on and so forth. Okay, so at these certain levels, the electron has to be moving at a certain speed, or, as you saw in the simulation on your computer, the atom would go kaboom. Okay, now the Bohr model makes it easy to view this, and with hydrogen, the different colors we see on the line spectrum are actually, for the red, the transition from n equals 3 to n equals 2, and then the green one 4 to 2, and then the blue one is the transition from 5 to 2. And I will show you how to calculate each of these wavelengths to show how each one corresponds to a color. Okay, so with hydrogen, the only colors you see are those energy transitions from a higher energy level to the second energy level. None of the transitions to the first energy level correspond to a region to a color in the visible region. Okay, all those wavelengths are outside the visible region. And this, in terms of the circular orbits around the atom, makes it easier to visualize. So for each one, we're going from a higher energy to a lower energy. So this is the n3 to 2, this is the 4 to 2, and this is the 5 to 2. So remember, the farther from the nucleus you are, it corresponds to a higher energy. Okay, then tomorrow I will show you how to calculate this wavelength, which corresponds to each of these different colors like red, green, and blue. Alright, that's all for today. See you next time.